Welcome to lecture number 9 for ECE476, Advanced Embedded Systems. In this lecture, we're looking at analog inputs and outputs. For example, on analog inputs, here I'm using the joystick on your development board, and on the left-hand column, you can see the voltage that's coming in. So we can read 0 to 3 volts in the X direction, 0 to 3 volts in the Y direction, and the temperature of your Pi Pico board. So we'll be reading analog inputs. We'll also produce analog outputs, so I can produce a sawtooth wave or half-rectified sine wave. So that's where we're heading. And as a reminder, this is part of Bison Academy. If you need a refresher on some electronics or circuits or embedded systems concepts, just go to Bison Academy and you have access to all the lectures in electronics, like doing analog inputs, filtering, stuff like that. For this course, Advanced Embedded Systems, you've got access to all the various different lectures. So if you need to go back and remember, how do I do this? This has the lectures, videos, and sample code. We are right here on lecture number 9, Analog I/O. So that's kind of where we're heading. As an introduction for analog inputs and outputs, up to now we've been dealing with binary inputs and outputs. The real world, however, is analog. Voltages can take on any value, not just binary 0 volts to 3.3 volts. Resistances can take on any value. Temperatures can be any value. And microcontrollers like the Pi Pico usually allow analog inputs as well as analog outputs. And a couple some terminology. A to D is the analog to digital reading. The digital portion is the microprocessor world. The A to D is for sensors. I want to find out what's happening in the real world, convert that to a digital number so the Pi Pico can read it. The D to A is the Pi Pico talking to the real world. Takes the digital signal from the Pi Pico, produces the analog voltage, signal drive motors, lights, stuff like that. This lecture looks at how to read analog inputs and drive analog outputs with a Pi Pico. So let's start out with the analog inputs. With the Pi Pico, there's actually 5 12-bit A to D ports in the Pi Pico. 3 of them are connected to I/O pins. You've got analog 0, 1, and 2. Analog 3 is not connected. Analog 4 measures the temperature of the Pi Pico. So really you just have 3 you can play with. And 2 of these are tied to the XY joystick on the GeeekPi Pico Development Board Kit Plus. So let's start with those 2. Let's read the analog inputs, analog input 0 and analog input 1. In terms of software, what I need to do is import the routine ADC, that's the analog to digital converter. I'll then define, I want to use ADC channel 0, that's pin 26, ADC channel 1, that's pin 27. These are hardwired to the XY joystick. And what they read is 0 volts reads 0, 3.3 volts reads a 65,000. Now this is a 12-bit A to D, so 12 bits actually only goes to 4095, but I can left justify or right justify that. When you do a read, I'm always going to get a power of a multiple of 8. So when we actually do a read, I get a 16-bit number. If I right justify it, I get 12 bits over here. That gives you the number 0 to 4095. If I left justify it, I get the 12 bits over here, and it's padded with zeros. That gives you a number between 0 and 65,000. Now, left justified, one of the reasons to use left justification is it's kind of independent of the number of bits. The lowest reading is always 0. The highest reading is always 65,000, regardless if I have a 10-bit, 12-bit, 14-bit, 16-bit A to D. So that makes the code more transferable. So that's kind of why left justification is a standard. You could right justify, but I'm going to kind of stick with the standard in this course. Have everything left justified. So full scale, 3.3 volts is 65,000. In terms of hardware, the way the joystick is connected, I've got a potentiometer. One side is tied to 3.3 volts, other side is tied to ground. As I move the potentiometer up and down, the wiper moves up and down. And what that does is when I push the wiper all the way up, I read 3.3 volts. Push the wiper all the way down, I read 0 volts. Likewise on the left-right wiper. And you can see that in the code. Well, actually, before we get to that, I can convert the A to D reading to a voltage. Again, 0 reads to 0 volts, 3.3 volts reads to 65,000. So likewise, when I read the analog input, I can scale it and get a voltage. And the scaling would just be A to D goes 0 to 65,000. It's this percentage of 65,000. Full scale is 3.3 volts. So there's my scalar. And the resolution then is just this number. The A to D can change by one count. They're integers. The ratio is 0.8 millivolts. So that's the resolution on this A to D. I can read voltage to 0.8 millivolts. That's for channels 0 through 2. Channel 4 actually reads temperature. And the conversion from A to D reading to temperature is this. That's from the data sheets. So we can also tell you the temperature of your Pi Pico, if you care. So let's try that. Let's write a program where I display the raw reading and then the voltage. So what this program does is it pulls in ADC from library machine, then defines the 5 analog inputs, and my scalar to convert A to D reading to voltage. I'm going to read 3 of the channels, channel 0, channel 1, and channel 4. That's defined up here. I will then, for now, just display the raw readings. If I move the joystick over here, if I go up, you can see the second column goes to 65,000. That's full scale. Go down goes to 0. Left and right. Here's left, 0 volts, and right, 3.3 volts. Now, if instead I display voltage, that's my scalar, multiply the raw reading by 3.3 over 65,000, that gives me voltage. Or this equation gives me temperature. As I vary the potentiometer, the second column goes 3.3 volts to 0 volts, left and right. Left is 0 volts, right is 3.3 volts, and temperature is just whatever it is. It's kind of toasty in here. So with that, I can read analog voltages. Now the A to D only reads 0 to 3.3 volts. If I want to read a different range, I just need to add a little bit of circuitry to the input, and then I can read different voltage ranges. For example, if I want to read 0 to 10 volts, just build a circuit that converts 10 volts to 3.3 volts. One way to do that is just 2 resistors. Do a voltage divider. This could be 2-to-1 ratio, 2K, 1K, 20K, 10K, 200K, 100K. Doesn't really matter. Do a voltage divider. That'll convert 10 volts to 3.3 volts. Now when I read full scale is actually 3.3 volts here, or actually 10 volts at the input. I can read 0 to 10 volts. And in terms of coding, everything stays the same, just change the scalar multiplier so that full scale means 10 volts. I can read minus 10 to plus 10 volts. So this one's a little bit trickier. There are a couple ways of doing it. The approach that I like is just to use 3 resistors because it's a whole lot easier getting 3 resistors to work than an instrumentation amplifier, and really that's all you need. What I'm going to do is use 3 resistors as a weighted average. So kind of the way this works, suppose I have signals A, B, and C, and the output Y. That's going to be my A to D output. If all these were the same, R, 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 then Y, by symmetry, is just the average of A, B, and C. So it's A with a weighting of 1/3, B is a weighting of 1/3, C is a weighting of 1/3. If I want to have A have a weighting of 2, I could just have 2 resistors. And now I have 4 inputs, each has a weighting 1/4. A has a weighting of 2/4, 1/4, and 1/4. When I put 2 together in parallel, that's essentially take R divided by 2. So this is the same circuit. That is a 2. Doesn't look like it. That's a 2. Or in general, what I can do if I want to have a weighted average, This is the weighting on A. Here's the weighting on B. Here's the weighting on C. I can do a weighted average just by changing the resistors. So that's kind of the idea. When I do that, they need to add up to 1, because if A is 1 volt, B is 1 volt, C is 1 volt, then no matter what, Y is going to be 1 volt. So that's kind of the idea. So let's do that. Suppose I want to convert minus 10 volts to plus 10 volts in, to 0 to 3 volts, 3.3 volts out. If I write the equation for that, I can rewrite this as Y is X plus 10, that brings minus 10 to 0, times 3.3 over 20. So the left endpoint, minus 10 goes to 0, Y is 0, that's good. When I'm at plus 10 volts, I want to go to 3.3 volts. So 10 plus 10 is 20, over 20 times 3.3 is 3.3. So this will go 0 to 3.3 volts as X goes minus 10 to plus 10. Multiply this out, I get Y is 0.165X plus 1.65. Now if I don't have a 1.65 volt source, let's assume I have a 3.3 volt source available, which I do on my PIC-board. So I could rewrite that as 1.165X plus a half of 3.3 volts. So this guy right there, that's my 3.3 volts. If I add up the coefficients, it doesn't add up to 1. So if X is 1, B is 1, Y should be 1. I'm missing a term. I can always add 0, so let C be 0 volts. The term I'm missing is 0.335. So add in 0.335C. If X is 1, B is 1, C is 1, the weightings add up to 1, Y is 1. That's good, that's what I want. Now change it. B is 3.3 volts. C is 0 volts. X is my input, minus 10 to plus 10. And now Y goes 0 to 3.3 volts as X goes from minus 10 to plus 10. These are my weightings, my weighting for A, B, and C. So the circuit then, pick your favorite resistor. I like 1Ks. The weighting on X will be 1K over its weighting, 6K. The weighting on B, that's my 3.3 volts, is 1K over 0.5, 2K. The weighting on C, that's ground, is 1K over 0.335, 3K. So build this circuit, that'll convert minus 10 to plus 10 volts in to 0 to 3.3 volts out. On the Pi Pico, I'll read 0 to 3.3 volts, or actually 0 to 65,000. 0 means minus 10 volts, 65,000 means plus 10 volts. Do a linear curve fit. And what that code looks like is this. Here's my scalar. It's a 20 volt spread for 65,000 counts. So the voltage is the raw A to D reading times my scalar minus 10. So 0 actually means minus 10 volts, plus 65,000 is 20 minus 10, plus 10 volts. So I can now read minus 10 to plus 10 volts. So basically that's pretty versatile. Any voltage you want to have coming in, the Pi Pico can read it. That's for the analog inputs. Let's look at analog outputs now. If I want to do an analog output, okay, to illustrate that, I've got my little Pi Pico board over here, and here's a potentiometer. As I change the voltage, I go from 0 to 5 volts. That's going into my voltage divider that goes to my analog input. Here I'm reading analog input 2, because 0 and 1 are the joystick. Here's the third analog input, displaying the raw voltage, and then the voltage going through the divider. And the divider should be 2/3, converting 5 to 3.3. Inverting it, the voltage on this side is 3/2 of the voltage on the left. So when I do that, here is the voltage that I'm reading, 2.3, and here's the actual voltage, 4.3 volts. So I turn the pot. I can change it to 1.98 volts. Reading is 1.95. .51 volts. Yeah, basically the same. Got a bad connection here. 1.06. And at the other extreme, 3.77. Okay, so I can read voltage. So that's kind of half of the equation, reading analog inputs. Now let's look at analog outputs. With an analog output, instead of just being binary, 0 volts, 3.3 volts, I want to output any voltage. So for example, suppose I want to output a half rectified sine wave. I want to go from 0 to 3.3, back down to 0. Output any voltage in that range. I'm just choosing a half rectified sine wave to give us something to look at. So in theory, there should be an infinite number of voltages between 0 and 3.3 volts. In practice, it's hard to do infinity. There's a finite number. Depends upon how many bits are on the D to A. So there's a couple ways of doing that. The first approach we'll look at is using pulse width modulation. From before, the machine library has a PWM function. With that, I can output a square wave with any frequency, any duty cycle. Again, the duty cycle is the percentage of on time. For example, this would be like 1/4. This would be like 25% duty cycle, whereas this would be a 90% duty cycle. What that does for you is the peak is always 3.3 volts. You're kind of stuck with that. The minimum is 0 volts. If I vary the duty cycle, I can fake an analog output. I can get something between 0 and 3.3 volts and a percentage of that. So for example, suppose I want to output a 1 kilohertz square wave. 1 kilohertz kind of a random frequency, high enough that I won't really see it with whatever I'm looking at. And vary the duty cycle. If I make the output 10%, again, 10% of 65,000 is 6553. Use the following code. I will output a pulse width PWM signal on pin 16. Well, pin 16's output, it's a PWM signal. The frequency is 1000 hertz. And here's the duty cycle. It is 10% of 10% duty cycle. The voltage I should read is 10% of 3.3 volts. So let's try that. Let's do the pulse width PWM is 10% of 65,000, 10% of 3.3 volts. What I get out is 0.33 volts. Let's try 20%. 0.659. Let's try 1 volt. So this should be 1/5. Full scale, should get 1 volt out. No. 1 over 3.3. I've got to keep remembering this is a 3.3 volt device. That percentage of 3.3 volts should get 1 volt out. Try it. There's my 1 volt. Let's try 2 volts out. About 1.5 now. 1.5 volts out. 2 volts. Now really, if you look at the output on pin 16, this is actually a 1 kilohertz square wave. If I measure the AC voltage, I get 1.45 volts RMS. That doesn't really tell me anything. I've got a square wave. The peak-to-peak voltage is 3.3 volts. If I convert peak-to-peak to RMS, I get about 1.45 volts as I change the duty cycle. The AC voltage, what I'm on right now, doesn't really change. That's because the peak-to-peak is always 3.3. 3.3 volts peak-to-peak's got some RMS voltage. The AC voltage doesn't really tell you anything. Go back to DC voltage. That's the average. So to see what's happening, this is where oscilloscopes are really useful. If I look at the signal on an oscilloscope, it is 1 kilohertz. That's what it told it. The peak-to-peak is 3.3 volts, like that's what it is on a Pi Pico. The average is your DC voltage. So this is currently trying to put a 1 volt signal. If I go back over here, and let's make it 2 volts, run. See, the pulse width just changed. If I change it to 3 volts, it's pretty high percentage. Change it down to 0.5 volts. That's what PWM does. By changing the duty cycle, I can change the average voltage. That way I can kind of fake an analog output with a binary signal. Again, now I'm now at 0.5 volts, average-ish. Peak to peak doesn't change, still 1 kilohertz. So next, rather than outputting a DC signal, let's output a waveform. Just for fun, let's make it a half rectified sine wave. It's going to go from 0 to 3.3 volts, back down to 0. Let's do that using PWM. Now there's a couple ways of doing that. I could use the sine function from the math library, calculate that on the fly. That's a little bit slow, so what I'm going to do is use a lookup table. What the lookup table does is when I have 100 elements in the lookup table, I'll fill it in before I start. Actually 200 elements. The first 100 elements is just a half rectified sine wave that goes from 0 to 65,000. That's full scale. Back down to 0. I'll then have 100 zeros after that. So I've got 200 elements in my array. I'm going to spin through that array, counting a mod 200. Every 10 milliseconds, I'll go to the next element, and that'll do my pulse width. Now what that looks like, if you look on the oscilloscope, is going to be a pulse width modulated signal going from 0% to 100%, back to 0%, and staying off. It looks kind of noisy. Well, this has a DC term and an AC term. The AC term is your 1 kilohertz and the harmonics, producing the square wave. The DC term, or low frequency term, is my information. That's the half rectified sine wave. Come up with a way to give me the low frequency term while blocking the high frequency term. Well, that is a low pass filter. What I have is kind of two different signals. The low frequency signal, that's my waveform. The high frequency signal, that's the square wave. The low frequency signal in this case is 1 hertz-ish. It's the Fourier transform of a 2-second half rectified sine wave. So the first harmonic's at a half hertz, second harmonic, third harmonic, fourth harmonic, stuff like that. So it's, maybe 0.5 to 10 hertz, ballpark. The high frequency term is the PWM. That's at a kilohertz, 2 kilohertz, 3 kilohertz. It's harmonics. So here's the challenge for you. I want to pass the low frequency terms. That's your half rectified sine wave. Fundamental is half a hertz and its harmonics. Say it goes out to 10, go up to 20 harmonics. Reject the PWM signal. That's at a kilohertz and its harmonics. Come up with a filter that passes frequencies below 10, blocks frequencies 1,000 and above. That's a low pass filter. Now there's several different types. Probably the simplest is an RC filter. Not a very good filter, but it's simple. Pick the corner frequency, one over RC, somewhere between 10 and 1,000 hertz. I'm going to choose one of RC's 100, 16 hertz, because 100 is a nice number. And what that should do is give you this type of function. The output is gain times input. This is an RC filter with a corner at 100 radians per second. So the output is gain times input. There's the gain. At DC, when S equals 0, the gain is 1. That's good. At a kilohertz, find the gain. Well, at a kilohertz, plug in S equals J6280, and I get 0.016. So the harmonics at a kilohertz on up have a gain of 0.016 and smaller. Let's calculate what the output's going to be. Well, that's actually a really hard problem because the input is a square wave. I've got a low pass filter. Find the output. Well, again, that's not a sine wave. If I use phasors, I can use phasor analysis, but that's not a sine wave. So let's change the problem. This is a typical engineering solution. Let's pretend this is a 1 kilohertz sine wave with the same peak-to-peak voltage, 3.3 volts peak-to-peak. If I do that, I can calculate the output. Did that. So if I calculate the output, here's the gain. Let's pretend this is a sine wave, 3.3 volts peak-to-peak at 1 kilohertz. Find the output, I get 52 millivolts. So what I should get is a half rectified sine wave with noise on it. The noise is the high frequency terms, the PWM that gets through the filter. That ought to be about 52 millivolts peak-to-peak. Now that's kind of a back of the envelope calculation, what we typically do in electrical engineering. If you want to get more accurate, I need to look at the input being a square wave. Kind of a hard problem. One way to do that is use CircuitLab. Throw this in CircuitLab, apply 1 kilohertz, 50% duty cycle square wave. This is the output. The peak to peak is peak to peak. That's actually 80 millivolts peak to peak. I calculated 50 millivolts peak to peak, assuming a sine wave. Input is not a sine wave, but it's about the right ballpark. So that's how much ripple I get with an RC filter. If I apply that, here's what the output looks like. Again, it looks like a nice, clean, fairly clean, half-rectified sine wave, noise on it. The noise is my 1 kilohertz terms getting through the low-pass filter. That's one option. RC filters are easy, but they're not very good. A better filter would be build a second-order Butterworth low-pass filter with a corner at 100 radians per second. So to do that, 1 over RC is 100. This guy right here is K. K is 1 plus the ratio, R9 over R8. And K tells you the angle of the poles. I basically have 2 poles, complex number right there. The angle theta is 3 minus K is 2 cosine theta. If you kind of forget how to do that, well, you can always go back to electronics, 320 electronics. This is where we covered what we covered in filters. Filter designs, active filters, lecture number 36 and 320. Or just take it on faith in this class. So, if I want to have a filter with a corner at 100, that's 1 over RC. Pick R, solve for C, or pick C, solve for R. To set the angle, that's the gain K. 3 minus K is 2 cosine theta. For Butterworth filter, I want the angle to be 45 degrees. Solve for K. So grind it all out. Here's what I want. K should be 1.58, and 1 over RC is 100. And if I do that, I'll have a ripple, plug in 1 kilohertz, times my input, 3.3 volt peak to peak, square wave, sine wave, at 1 kilohertz. The output should now be 1.3 millivolts, about 50 times better. So Butterworth filters are far better, a little more complicated, but much better. So now when I do this, I should have my half-rectified sine wave with a little bit of noise on it. The noise will be about 1.3 millivolts, peak to peak, noise on top of it. I can check that in CircuitLab, and it pretty much matches up. CircuitLab says it'll be 1.6 millivolts peak to peak. Yeah, not bad. If I try it in hardware, that's what I get. Okay, so let's see what that looks like. This is a bad ground. You fix my ground there. This is what the PWM signal looks like. It's your half-rectified sine wave, pulse width going from 0% to 100%. Here I slowed it down. So you can see the pulse width going 0 to 100. That supposedly is a half-rectified sine wave. Run it through a Butterworth low-pass filter. That's over here. There's my Butterworth second-order low-pass filter. And what you see is a little bit of ripple. That's what's getting through the filter. If I slow it down, you can see the half-rectified sine wave. It's going up, coming back down. I'm bringing down the DC signal. There you can see it. So I have an analog output. So that's with the PWM output. And actually, with the Pi Pico, it's really designed for PWM output. It is really, really convenient to output analog voltages using PWM. So that's the main way that we do it nowadays. There are other options. For example, there's the MCP4921. That's a D2A chip that we used in embedded systems. 376. This is a chip that's a 12-bit D2A. You send it serial data, and it ships out a voltage between 0 and VDD. For this chip, VDD could be anything between 2.7 and 5.5 volts. It has the SPI interface, $2.81 cost as of this summer, so June 24. So like the A to D, the D to A's output is proportional to the number written to it. This is a 12-bit D to A, so full scale is 2 to the 12th minus 1, 4095. The voltage I get will be that percentage of it. The VDD could be anything between 2.7 and 5.5 volts. Again, 5 volts, 5.5 volts will not hurt the Pi Pico because everything's output to the chip. There is no input. So it's not going to actually hurt your Pi Pico. You could pick whatever you want. You could say 5 volts. The connections would be connect the serial port to the MCP4921. This is SPI data, so I need a chip select, the clock, and data. I need to give it power and ground, of course. Then the output is on pin 8. To send a 12-bit number, I actually send 16 bits. The number that I send is bits number, well, these bits, the last 12 that I send. The header lets you set it up. There's different ways of setting it up if you check the data sheets, or just take it for granted. I want the input to be 0011. What that does is it makes the output proportional to the input, and the max scaling is your power supply, VDD. So it'll go after 0 to, if it's a 5 volt power supply, 0 to 5 volts. To send the data, chip select goes low, then high. For each bit, I pulse the clock, valid on the falling edge, and you get your data. And there's a couple ways of sending out that data. I can use bit banging, just brute force it. I want to send a number to it, 0 to 4095. It receives that data, replaces the high 4 bits with 0011 or 3. This is your data, the low 12 bits. Brings the chip select low, starts with clock being low, and then sends out the most significant bit of X, pulses the clock. Next bit pulses the clock, does that 16 times, bring chip select high, and you're done. So if I do that and just count 0 to 4095, I get a square or a sawtooth wave. So on a lot of function generators, a sawtooth wave is one of the options. I don't really know what you do with it, but it's really easy to generate with the D to A. You just count. And the voltage, the peak voltage, is whatever my VDD is. In this case, it was 3.3 volts. Could be 5 volts. It's not going to hurt the Pico. If we look at the clock line and the data line, here's the data being clocked in. That's the clock line. Here's my data. So in this case, the data was a 1, actually 0, 0, 1, 1. That's binary 3. 1, 1, 0, 1, 0, 1, 0, 0. This is the voltage that I want to output. So that's using bit banging. I can also use the SPI port. The SPI port is actually a better way of doing it. It's a little bit easier. I just set up the SPI port. In this case, I want polarity being 0, meaning the clock line idles low, phase being 1. It's valid on the falling edge, 8 data bits, and this is the SPI port. SPI port 1 is pin 10 is clock, 11 is master out, 12 is master in. Let's see. Okay, set up your data. So the first 4 bits are 0011 or 3. To use the SPI port, my data has to be in a byte array. So I'm going to take my data, start with an empty array. The first 8 bits are the most significant bits. The next 8 bits, the least significant bits. Bring chip select low, send out the SPI data, bring it high, and you got your data. And the beauty is I can do it much faster. This is sending the data at 10 megahertz. Kind of depends upon how you're setting it up. On a breadboard, you can do 10 megahertz. Occasionally on the breadboards with all my loose wires, I've got more capacitance. I might have to drop that frequency. But on a breadboard, you can definitely do 10 to 40 megahertz. What the data looks like on my oscilloscope is this is kind of pushing my board. I've got some capacitance. That's a square wave with some capacitance on my wires. This is the data. It is getting through, but that's kind of pushing the limit. All right, so showing how that works. Here I've got, this is just the Pico board. You can use the Pico board Plus. It's got a convenient breadboarding area. Got the wires connected up to the 4921. The data comes in on the blue wire. The data voltage out is on pin 8. On the oscilloscope, you can see I'm counting and getting my nice triangular wave as I count. So let's illustrate that. Let's output 2/5. I've got my 4921 connected to 5 volts. 2/5 full scale is 5 volts. Try that. And what you get is 2 volts. Okay, let's try 1/5. I get 1 volt. Let's try 1.5 over 5. Let's try that again. Three-fifths. Okay, 3 volts. I got something weird going on. So anyway, I can output analog voltages. Yeah, I'm afraid it paused because it's been locking up videos too long. So anyway, that's the D to A. If you want to put more voltage, like -10 to +10, just use an instrumentation amplifier. For example, this one has a gain of R1 over R2 times A minus B. If the input is 0 to 5 volts, I want Y to be 4 times X minus 10. Or rewriting it, it's 4 times X minus 2.5. Make this a 4-to-1 ratio, 4K, 1K, 4K, 1K, anything 4-to-1. X goes right here, so this is your D to A output, 0 to 5 volts, and this is 2.5 volts. Do that, I'll go from -10 to +10 volts. So in summary, with a little bit of coding and some hardware, it isn't hard to read analog voltages. It isn't hard to output analog voltages. When using a chip with an SPI input, you can use bit banging to drive this device. Bit banging is nice because you've got complete control over what's going on, but it tends to be slow. If you're willing to figure out the SPI port, it's actually much easier, and you can send data much faster at 10 megahertz. But with that, you now have access to analog inputs and outputs. That's lecture number 9 for ECE476.